Okay? But if I were to move the projector the same distance away, backwards again, it would be 4 times dimmer than this now. It works with light. It works with lots and lots and lots of things. All right. Killing it. Okay, take a look at figure 8 here. I'll pull it up for you. Number 7. It's basically just what I showed you. Oh. So if you go out one distance, you have one amount of area. Okay, he's using a paint sprayer can. If you go out double the distance, it's 4 times. If you go out 3 times the distance, it's 9 times. If you go out 4 times the distance, it's 16 times. It's always the distance squared. But since it's the same amount of stuff, it goes less. So you have the same amount of paint, but it's spread out over 16 sheets of paper. Each sheet of paper is going to get less paint than it did before. 16 times less paint than the first one would. Okay, so if you drew my example, you wouldn't need to put anything for 8. You can just see picture in number 7. Otherwise, if you want to draw a diagram of what I kind of looked like here, that would be helpful. All right, number 9. Let's say you take a dumbbell which has a force of gravity of 320 on Earth, out a distance 4 times further. What would the force be? So force should be 4 squared less. So 4 squared is 16. So 320 divided by 16 would be 20 newtons. That's how much it would weigh. 20 newtons if you went 4 times further out. Michael, pull your mask up. Thank you. All right. Almost done, then we'll take a short little break. All right, what is weight? So weight is the force of gravity by a planet on an object. See, weight is specifically just for acting on planets, right? Well, if we talk about the force of gravity, we're talking about between any object. But when we're talking about weight, we're really only talking about the force of gravity on us from Earth or the Moon or Jupiter or something like that. So what determines what we feel? That's the normal force. So normal force, we've talked about this, normal force is what you feel. Normally, Fg and Fn are equal to each other. Normally, they're the same. They're not always the same, but they're frequently the same. So, if you have normal weight, the normal force up and the force of gravity down are the same. If you feel heavier, then the normal force is larger than gravity, which hasn't changed, it's the same value. If you feel lighter, the force of gravity is larger than the normal force. So what would happen if you feel weightless? Well, we talked about this in that last reading you did in Activity 2. Weightlessness is when there's no normal force. So why do astronauts on the International Space Station feel weightless? It's not because there's no gravity. There is gravity. It's because there's no normal force. In other words, they're in free fall. This person feels no normal force. They feel weightless because there's only gravity. There's no normal force. A person on the space station feels weightless because there's only gravity. There's no normal force. But because everything is that way, they feel weightless, and everything looks weightless here. So let me show you a couple of videos here as a little bit of an example. There we go.
If you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung-out cloth? So, and I had to use equipment that was here on board the space station. We might have the coolest washcloths ever here on the space station. I'm going to show you.
Something to point out that's not obvious, but is my favorite thing. You'll notice frequently that he'll just let go of the microphone. It'll just hang there. Again, the reason why he's weightless is because everything is falling, but they're falling around the Earth, and they're falling together. So there's no normal force. There's no feeling of weight.
This is what I'm going to use for the experiment today. And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out. Merritt and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth.
The reason why things are floating and not staying exactly in the same place is because any motion will move them and accelerate them.
Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet.
So you can see the water doesn't fall out like you would expect because there's no normal force. So the reason why things fall on Earth is because we stay still and gravity pulls things down. But if gravity's pulling us and the water down, then everything falls together and the water stays in the same place.
The water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand.
So kind of a fun little demo here. Let me show you one more. This one's just kind of silly. Okay. First of all, you're going to think that this isn't real, but I assure you that it is. So this was an actual experiment done by the U.S. military in the 50s. What they were doing is they were trying to figure out what would happen to cats if you dropped them in space. Not making this up. So what they did is they dropped cats under normal gravity, so you know that cats will rotate to land on their feet. So what they were saying is if there's no gravity, if there's no falling nature, and again, there is gravity, it's just you don't notice it. So if there's no falling nature, then what will happen to these cats? And I'll show you here.
In these experiments, you can see the disorientation resulting when an animal is suddenly placed in a weightless state. Cats, when dropped under normal conditions, will invariably rotate their bodies longitudinally in midair and land on their feet. This automatic reflex action is almost completely lost under weightlessness.
So you can see the cats are still able to rotate, but because they're not falling in the sense of what you would normally... Yeah, that guy just kicked the cat into the ceiling, you're right. Anyway, don't ask me why someone did that as an experiment. But someone was sitting around saying, you know what we really need to find out? What happens to cats if you drop them in space? And there you go, that's what happens. They can still rotate, but because they're not falling in the sense of what you would normally think, because they're weightless with everything else, you don't notice any change because they're falling at the same rate other things are falling. And so the cat's trying to flip itself around, and it's never going to get to a point where it can actually land on its feet. Part of the problem is cats have an internal mechanism to kind of record falling and figure out what's up and what's down, and they can use that to rotate and then stop their rotation. When you get rid of this idea of normal force, you can't really determine that. And so the cats have trouble figuring out what. It also doesn't help when people kick them into the ceiling, but there you go. All right, any questions?